Number 3, potential due to an electric dipole. The potential due to an electric dipole at any distance r at angle theta from the axis of dipole will be given by 1 over 4 pi epsilon naught q over r plus minus q over r minus. So this is what the potential is going to look like, and in the limiting case when r is much greater than d, potential will be 1 over 4 pi epsilon naught p cosine of theta over r squared. Now how do we come up with that answer, right? It seems like a huge step to go from that expression q over r to p cosine of theta. So let's talk a little bit more about it. So if you have a dipole, what does a dipole consist of? It consists of a plus charge and a minus charge. And in a dipole, the charge goes from minus to plus, right? So if you have a point P, at which we have to find the potential, how do we do that? Well, if you place the origin at the center of the dipole, it makes life easier for us, right? And then you draw a line from your middle of the dipole to the point P at which we have to find the r and call it r. And this angle we're going to call theta, okay? So then the potential is going to be given by k q over r plus minus q over r minus. Good? What does that mean? That means this distance is r plus and this distance is r minus. Okay? So for many applications, P is much greater, or r, the distance between, so r is much greater than d. Okay? For many applications. So yes, here it does not seem that way, but in most cases, r is much greater than d, where d is the distance between the dipoles. So in fact, what I can do is, if this is much greater than this, then I can write r plus minus r plus, minus to be equals to d cosine theta. Okay, how do I do that? Let's talk a little bit more about that. So I'm going to change this marker and I'm going to redraw this. So if I was to draw a perpendicular from this point to here, what do I get? This angle will be r minus r plus. Agreed? So if these two are the same, then this distance here is r plus minus r minus r plus, right? Or, so I should rewrite this as approximately. And why should I rewrite this as approximately? It's because if I look at it very carefully, if this is my angle theta, then this almost is the same as angle theta, provided this condition holds true, right? So if this condition holds true, what is cosine of theta? Cosine of theta is r minus r plus divided by d. Again, noting that these two will be the same angle only if and if only r is much greater than d. So I can rewrite this expression as d cosine of theta. And also, I can say, because r is very large, I can almost say that r plus and r minus are almost equals to r. So they are almost equal to each other. So in that case, I can write r plus times r minus is almost the same as r squared. Again, only in this limiting case will these two things hold. Okay? So in that case, once we have that done, can I rewrite my expression, this one, as and simplify it to give me KQ R plus R minus minus R plus, right? And then I can plug this value in here and this value in here to give me KQ d cosine theta divided by R squared, right? Now, V, this implies V equals KQ d cosine theta divided by R squared. Or this one right here we know equals P. So it'll be P cosine theta divided by R squared. This expression is the same one as you see that you saw on the PowerPoint, except the K is obviously written as 1 over 4 pi epsilon naught. Now let's do an example. An electric quadrupole consists of two electric dipoles arranged such that they are almost but not quite cancel each other in their electric effects at distant points. Calculate VR for points on an axis of this quadrupole. So, in this case, our quadrupole consists of Q, 2Q minus Q and Q. And it's asking me to find the potential at this point. Okay? So this means this is Q, this is Q, this is, sorry, minus Q, and then this one is going to be Q. Okay? And it says that the distance, as far as I can tell, between these is D, and then between these is D. And if I consider this distance to be R, then actually it might make sense, as the picture says, it might make sense to draw it this way. So if this point from the center is R, then this distance is R minus D, right? This distance right here is going to be R minus D. And then the distance between here and here, all the way to the top, will be R plus D. Okay, once we have those figured out, so I have this distance being R minus D, this distance being R, and this distance is R plus D, it makes our life a little bit more easier. Okay, so what do we know? So for point P, V will be given by K sigma n Qn over Rn. Okay? That we know from superposition. Makes life easier. Okay? That means I have to account for each of the charges, and since there are 4 charges, then I have to account for all 4 of them. So what I will end up getting is going to be K. I'm just going to take K common out. I'm going to start with Q at the top. Q over R minus D, right? That will give me my first Q1 and R1, right? Plus, this is going to be my second one. It is going to be minus 2Q divided by R, okay? And my third one is going to be Q divided by R plus D. And that is going to be my superposition. And then all that requires for us to do is KQ 1 minus 2 plus 1 R minus D over R, R plus D. Now I have to take some LCMs, do a little bit of algebra, solve it, and I come up with an answer. So I'll do the first step, and then I'll leave the rest of the steps to you guys, for you guys to do. It's going to be R minus D, R, R plus D. This is going to be R, R plus D, minus 2, R minus D, R plus D, plus r and r minus d. Now you just have to do a bunch of algebra, calculate all of these terms. So I'm going to leave those up to you. And what you should end up with is going to be kq 2d squared over r cubed 1 minus d squared over r squared. Please make sure that you are able to do this bit of algebra. Now, for the limiting case where d is much, much smaller than r, what will happen? We can ignore d squared over r squared, can just pretty much be ignored. So we can ignore this. Again, in a limiting case, when this is true, this expression will reduce down to k q 2d squared divided by r cubed. So in the limiting case, when d is much, much smaller than r, so d is much, much smaller than r, your expression for a dipole will become that.